So here we have a basic combinatorial proof problem, showed left-hand side equals the right-hand side. And a combinatorial proof has four parts. 1, you come up with a story. 2, you show what the left-hand side is counting. 3, you show what the right-hand side is counting. And 4, you conclude that because the left-hand side and the right-hand side are counting the same thing, this equality holds true. So the proof structure is super straightforward, but I think the hardest part to combinatorial proof is getting started and figuring out what the story even is. So my advice is, before you do any writing, analyze the equation. And when doing analysis, I like to look at the side that's less complicated. So in this case, the left-hand side definitely looks less complex. There's a lot less items to look at. There's no n-1s, n-2s. So we're just going to ignore this right-hand side completely, and we're going to only look at the left-hand side. So the left-hand side is 3n choose n times 2n choose n times n choose n times n cubed. So let's figure out what the story is based on this left-hand side. What immediately stands out to me when I look at this is, if we ignore this n cubed for now, just look at only these three items, we're starting with 3n items, and we choose n from here, and then once we choose n from there, the next successive number of items we're choosing from also decreases by exactly n. So it's going from 3n, and after you choose n, there's 2n items left to choose from, and once you choose another n, there's only n items remaining from which we choose the final n. So to me, it seems like we're counting the number of ways to choose 3 distinct n-size groups of objects from a pool of 3n objects. And that would account for these three things. But what does this n cubed mean? Well, whenever you see an exponent in combinatorial proofs, sometimes it might be useful to break it up, and that might make it more obvious what's going on. So here, let's break up the n cubed into n times n times n. And remember, we just determined that this side over here means we just chose 3 groups of n. And notice how we just broke this up into 3 n's being multiplied together, 3 and 3. So it matches up. So I get the impression that each of these n's is probably associated with one of these 3 groups. So let's rewrite this so that it could be more obvious. I'm going to sandwich the n's in between each of the combinations. Now that we've rewritten like this, I think it becomes slightly more obvious that with each of these groups, we're choosing one item from each group, because each group is size n, so that's where the n times n times n comes from. And that's our analysis. So now we understand what's going on. We're counting ways to pick 3 groups from 3n, and from each of the 3 groups, we pick one item. And now we can translate this into a story and begin our proof. So 1, story. Since we're breaking things up into groups, my go-to combinatorial proof story is talking about sports teams. So translating what we analyzed earlier into the story, let's write, the story is counting the number of ways to divide 3n people into 3 distinct teams, team 1, team 2, team 3, of n-sized people, where each team has one captain. And there we go. That's our story, which we got from analyzing the left-hand side of the equation. And since we derived our story from the left-hand side, this next step is really easy. We already did this. We just need to formally write it down. So 2, left-hand side. Let's start by dividing the teams up. There are 3n choose n ways to pick team 1 from 3n people, 2n choose n ways to pick team 2 from the remaining 2n people, and finally, there's n choose n ways to choose team 3 from the final n people. Now, from each of the teams, we choose a captain, where each of the 3 teams has n ways to choose a captain. And that gives us the left-hand side of the equation, which is 3n choose n times 2n choose n times n choose n times n cubed. Now let's go on to the right-hand side. We skipped over this side earlier because it was more complex, but now that we have a story, we know what we want to show it's counting. So the only tricky part left is showing how it's counting in this story. Remember, we're showing that when we're showing what the right-hand side is counting, it must be consistent with the story we used with the left-hand side. If the right-hand side and the left-hand side are not consistent in their story, the proof is not valid. So as we start to analyze the right-hand side, let's keep the left-hand side story in mind. So here, the first item on the right-hand side is 3n choose 3. How does this fit into the story we have? Well, from 3n, we're choosing 3 people, and where else did we do that? It was choosing the captains. We chose 3 captains in all. So it looks like on the right-hand side, we're actually starting by choosing the 3 people to be the captains. And then it follows that the 3 factorial here is just counting the number of ways to assign which of the 3 captains go to which of the 3 teams. So if the first captain goes to team 1, team 2, or team 3, the second captain goes to team 1, team 2, or team 3, and so on. And before we go to the next part, let's remember what's left in our story. We've already picked the captains, so the only thing that's left now is to pick the teams themselves. And if we look at this next part, we notice how it looks almost exactly like the left-hand side earlier where we chose the 3 teams. Except instead of choosing n people, we're choosing n-1, and instead of choosing from 3n, 2n, and then n, we're choosing from 3n-3, 2n-2, and n-1. Why is that? Well, unlike the left-hand side, we already figured out who the captain was, right? So we don't need to choose n people per team. We only need to choose n-1 people per team. And since the 3 captains were already chosen from the 3n, the pool of people to choose from is only 3n-3 people to start with, not 3n. So we can confidently say that 3n-3 choose n-1 is the number of ways to fill in the rest of team 1. 2n-2 choose n-1 is the number of ways to fill in the remainder of team 2, and n-1 choose n-1 is the number of ways to fill in the rest of team 3. And that gives us the right-hand side. And we're almost done. We just now have to conclude, since the left-hand side and the right-hand side count the same thing, it must be the case that the left-hand side equals the right-hand side. And that's the combinatorial proof. They're not hard, but there's a lot to do. And if you break it down and analyze it little by little, they're actually pretty straightforward.